about 3 or 4 years ago in collaboration with Dr. Marcelo Nogueira Barbosa and also with Dr. Paulo Mazzanzini. And the primary researcher in this project is Eduardo Ribeirão. Eduardo started working on this project as part of his bachelor's degree project and is now close to completion of his master's project on this, and is also interested in continuing for a PhD on the same project. Okay. Okay. So this project is in collaboration between the University of Calgary and the research group at USP here. The main interest in this project is on the detection and analysis of compression fractures in vertebrae. Vertebral fractures are important indicators of a few conditions and diseases, including osteoporosis, and insufficiency fractures are usually seen as a partial collapse of some of the vertebral bodies. In addition to visual analysis of the radiographic images obtained by radiologists, some form of quantitative or even semi-quantitative analysis would be useful in the assessment of spinal and vertebral deformities, including fractures, and could assist in the diagnostic decision-making process and guiding therapeutic procedures. Here is an example, an illustration from a paper by Gnan Wu. There are a few illustrations here. The mouse here. Excuse me. Yeah. The upper row here shows the same normal vertebra copied for comparison. Which one? Oh, okay, okay. Then the green arrow appears, is it? Do I have to pull the green arrow then? No. Okay, well, it comes wherever I go. Okay, here are 3 examples. Actually, they are the same vertebra copied 3 times, I believe. And the grading of mild fracture in row 2, where you see compression of the anterior portion or the middle portion or the posterior portion, and moderate fracture in the 3rd row, and severe fracture again in the anterior portion or the middle portion or the posterior portion of the examples shown here. So as you can see, the height of the vertebral body changes related to the extent of the fracture, and grading of fractures would therefore require measurement of the height of the vertebral bodies that have been affected by the process or the injury if it is due to traumatic causes. The images used in our study, which is still in progress, and the results are to be seen as results of work in progress. The results are obtained by processing lateral lumbar spinal X-ray images, which are planar projection images. There are a few studies reported by other research groups where computer tomography and even MR imaging have been used. But of course, computer tomography involves the use of a higher radiation dose, and MR imaging is too expensive and hard to access in many areas of the world. So lateral lumbar spinal X-ray images provide adequate information for this purpose, and the protocol here at USP includes the acquisition of these planar X-ray images, and the database prepared so far includes 41 cases selected by an experienced radiologist who is Dr. Marcelo Nogueira Barbosa here. 19 of the images are from patients with confirmed diagnosis of insufficiency fractures, and 22 are from a normal group. The images were digitized using a VIDAR Diagnostic Pro scanner at about 84 micrometers per pixel. So here are some examples. Here is an image of, I believe this is a normal case, where you see the lumbar part of the vertebral column, and the vertebral plateaus were marked in this manner by Dr. Marcelo Nogueira Barbosa, and the thickness of these lines is 5 pixels. And in the present study, the concentration is on L1 through L4 only. Now, our aim was to detect the vertebral plateaus automatically by using image processing techniques. And we are going to present some initial results that we have obtained for this purpose. We could possibly detect edges of vertebral bodies using edge detectors such as Sobel detectors or Canny operators that are commonly used in image processing. But it would be efficient to use filters that can be tuned to multiple directions. And Gabor filters offer the best option in terms of detection of edges or oriented features at all angles. And Gabor filters are wavelets, if you want to view them as wavelets, if they can be normalized for that purpose, or normalization may not be important. Gabor functions are sinusoidally modulated Gaussian functions. They provide optimal localization in both the space domain and the frequency domain upon Fourier transformation. So here is an example of a Gabor function or filter oriented at 45 degrees in the image domain. A Gabor filter is formed by taking a Gaussian, which is a bell-shaped function, and multiplying it with a sinusoid, a cosine function or a sine function. So the bell-shaped curve is modulated, so we have a main positive part of the bell, and then negative parts and positive parts that decay. And this is a two-dimensional function. And in this image, it is shown as an intensity image, where the positive main lobe is seen in white here in the middle, and then on either side, you have black parts that indicate the negative side lobes, and then there are positive side lobes. The filter has been oriented at 45 degrees and is anisotropic. That is, the variance of the Gaussian is larger in this direction than in the orthogonal direction. The Fourier transform of this filter is shown in the image on the left-hand side, where you see that the image is a bandpass filter. The low-frequency components at the center of this figure, which is a 0, 0 frequency in the Fourier domain, are rejected, and the medium frequency components are passed by the Gabor filter as indicated by the bright regions in this image. So the Gabor filter is a bandpass filter, and because this filter has been rotated, this function has been rotated to 45 degrees, in the image domain, the corresponding frequency components are passed, which are located at an axis of 135 degrees in the frequency domain. Now we can, excuse me. So here is an equation that indicates the parameters involved. We have a Gaussian function, which is the exponential. There is a sigma square x, which is the variance in the x direction, and sigma square y, which is the variance in the y direction. And there is a normalization factor here. And this function is multiplied by a cosine function with a frequency f. You can change it to a sine function if you want to detect dark edges or dark objects. And we have 3 parameters, sigma x, sigma y, and f, that need to be determined in accordance with the characteristics of the objects or edges you wish to detect. In the design that we have developed, the input given by the user is in terms of the thickness of the line to be detected. If you want to detect linear features. If you want to detect edges, then the thickness could be set to be very low. But if you want to detect objects of different thickness, then you have to set the factor tau according to that. What is the range of the thickness of objects you want to detect? And the elongation. How long is the line before the angle or orientation changes? And the orientation theta. But in many applications, we may be interested in detecting oriented objects or edges at all angles, in which case theta will be from 0 to 180 degrees. So we can relate the specifications given by the user in terms of the frequency f as 1 divided by tau, and the sigma x as tau divided by a normalization factor, and sigma y, which is the variance or standard deviation in the other direction, as L times the elongation times the standard deviation in the x direction. So in this manner, the parameters that are specified by the user are converted to the Gabor filter parameters. And then to rotate, you apply a geometric transformation to each angle theta for which you want to apply the filter. In our study, we use a bank of 180 Gabor filters, one for each degree from 0 to 180 degrees. So here are some examples of Gabor filters. The upper row shows the impulse response, or the filter in the image domain, the point spread function. So this is a horizontally oriented Gabor filter of some thickness, and the Fourier transform is shown below that, where frequency components in the vertical direction are passed. If you increase L, elongation, the filter becomes longer in the direction of the filter, and the frequency response becomes narrower. So it's a narrow band pass filter. If you increase thickness tau, then the filter, the main positive lobe and all the side lobes of the Gabor filter in the image domain become thicker, and the frequency response is moved towards the lower frequencies. If you rotate in the image domain, in the frequency domain, there is a corresponding rotation. So we can choose the appropriate values of tau and L according to your application, and start with a basic filter and then rotate it as desired for all angles. So the image needs to be filtered for all angles of interest. So here is an example of filtering of a retinal fundus image. I wanted to show some other application where you can easily see some oriented structures. So here is an image, a retinal image, where you see the blood vessels in white. It's been pre-processed into the intensity channel and inverted, so blood vessels appear as bright lines. And this is the Fourier transform on the left-hand side, where you may be able to, you need to turn the lights off if you want to see the details. Could you turn the lights off, please? Or if you have the PDF file and zoom into this part, you see oriented segments of energy. For example, along approximately 45 degrees, you see a peak, a line, approximately a line oriented that way, which will correspond to the blood vessels at approximately 135 degrees in the image domain. There is a 90-degree difference between the angle as you see in the image versus the corresponding components in the frequency domain. Now, if you were to apply a 45-degree Gabor filter, the magnitude response is this, where only the blood vessels oriented at 45 degrees are extracted, like here, like this part and this part. And the other blood vessels, such as these, are not detected. If you change the parameters, the thickness, if you use a larger thickness like 8, then you detect the entire blood vessel. If you use a small thickness like tau equal to 2, you only detect edges. And the elongation also affects the detection in terms of the intensity over the length of an oriented structure. And here is an example for theta equal to minus 45 degrees, where the other blood vessels have been detected at approximately minus 45 degrees. Minus has changed here. I'm sorry, the symbol has changed in conversion. So here is the original retinal fundus image, which is a color image, but we have applied for the detection of blood vessels, you don't need the color. The intensity is adequate, or the green channel is adequate. And in this image in the middle, the Gabor magnitude response, the maximum response for each pixel over the 180 Gabor filters that were applied is shown. I'm sorry, it has moved there. This is the magnitude response. And then In the third image, at every pixel, you see the angle that was detected by the Gabor filters, which is the angle of the Gabor filter that gave the highest response at that pixel. So you can see that for the blood vessels here, the angle agrees with the angle determined by the Gabor filter as you follow each blood vessel. So you can use Gabor filters not only to detect oriented structures in magnitude like in the central image, but you can also determine the angle of each oriented structure as you see in the third image. And this information can be used to derive multiple parameters. So in this project that Eduardo is working on, each image was filtered using a bank of 180 Gabor filters in steps of 1 degree. The width used was 4 pixels, and the elongation factor used was 8. For each pixel, the magnitude response and the angle of the Gabor filter that gave the highest output were used to compose the magnitude response and then the angle image. So here are some examples. This is the original image, and the arrow is jumping. Anyway, that's the original, and this is the Gabor magnitude image, where you can see the vertebral plateaus have been detected well, and also some marks that were written by the radiologist have been detected as edges. And other structures with uniform intensity have been suppressed. So the Gabor filters act as good line detectors or edge detectors. From the Gabor image, Gabor response rather, we can compute a few more features. There is a feature known as coherence, which was proposed by Rao and Jain, where you include the Gabor magnitude information, GMN, and the angle theta mn at every pixel in a small neighborhood around the current pixel being processed. So P here is a window of size 15 by 15 pixels that is applied to every pixel in the processed image. Excuse me. In the original work by Rao and Jain, G was the gradient magnitude and theta was the angle of the gradient at every pixel. Instead of gradient in this work, we use the Gabor magnitude at each pixel and the Gabor orientation or the angle of the filter as determined in the previous procedure that I described. The psi PQ here or psi PQ here is the average or dominant orientation at the pixel over the window. So in a neighborhood around each pixel, we check the Gabor magnitude response and the angle and obtain a weighted average. So this angle is the average angle or dominant angle within the small window, and cosine of theta minus psi here measures the variation in angle or orientation within a small window. If at all pixels the orientation remains the same, then this value will be high. If the angles are scattered, like in background and noisy areas, this value will be low. So this is called coherence. There is another measure that we have designed to capture a different measure of orientation strength, which may also be called alignment energy or coherence. But it's a different concept where we take the Gabor magnitude G square for all angles theta k going from 0 to 179 or 180 degrees, apply a weight of G square with cosine 2 theta and sine 2 theta, and then normalize this. The idea here is that if at a location there is only one dominant oriented structure, then there must be a high degree of alignment or orientation. If there are many intersecting structures, then this value will be low. So here are some examples. Before going to some examples, there is another step that I need to describe. 5 points were marked manually on every image for use as reference, labeled as P1 through P5, and these were marked near the middle of the intervertebral spaces. Is that one? Yeah, I can't read from here. So P1 is this point, P2, and so on up to P5. These were manually marked by using a mouse. And then The distances between the points were calculated automatically, and using 75% of these distances, the corresponding line joining the manually marked points was shifted in either direction parallel to that orientation to define a quadrilateral area, which is this area for each vertebra. So now we have the region of L1 through L4 delineated semi-automatically, in the sense the input required is 5 points, 5 clicks on the mouse by the user, and the rest is done, it is derived in the program. To detect the vertebral plateaus in the work being done by Eduardo, the pixels in the regions corresponding to L1 through L4, determined using the input I described just now, were obtained from the original image, the Gabor magnitude response, and the orientation strength, which has also been called coherence in this work. So for every pixel, there are 3 inputs which were given to a logistic sigmoid neural network, and a decision was made as to whether the pixel belongs to a vertebral plateau or not. The output of the neural network was used to label the pixels, and the neural network was trained using a Lee1 image out, or vertebral out. Lee1 image out. Okay, Lee1 image out procedure. I'm just confirming a few things with Eduardo here. So here is an example of a result obtained. This is the original image, and this is the output of the neural network, where you see the values, the output values for the various vertebral plateaus, and the corresponding manual annotation is shown here. The manual annotation was used in training the neural network, correct? Yeah. To assess the performance of detection, measure of overlap was computed by comparing the output of the neural network with the manual labeling as done by the radiologist, and receiver operating characteristics, or ROC curves, were derived by varying the parameters in the neural network to study the effect of various thresholds and parameters there. And the area under the ROC curve, the AUC value, was obtained as a measure of detection performance. The average overlap obtained was 91.7%. We are checking to verify if that was correct. And the average area under the curve is 0.8, which is quite good. So once the vertebral plateaus are detected, the next step is morphometry, which is to make measurements of shape for the detection and analysis of compression fracture. So here is, on the left-hand side, is an example of a normal case. These are manually labeled vertebral plateaus, where you see the thickness is fairly uniform for each vertebral body, such as there, here, here, and here. In the case on the right-hand side, you see that the thickness varies within each vertebra, and this is a case with compression fracture. To measure the variation in height for each vertebral body, the automatically detected result, which is shown here, was skeletonized, which is shown here, but if we were to draw the skeleton, there will be only 1 pixel thick and difficult to see. So actually this is not the skeleton, but the same image repeated. There is a skeletonization procedure to reduce each plateau to just a single pixel thick line, and then we obtain the convex hull. The convex hull is the smallest convex region that encloses all the automatically detected points. So the convex hull now gives the entire region covering L1 through L4. Now, to this we apply a skeletonization procedure, and it may be difficult for you to see unless you zoom the PDF file. There is a single pixel thick line here, which would be the medial axis that runs along the center of the convex hull, such that it is equidistant from the edges. So it is the central line of the convex hull, which is shown here. And at the edges of the skeleton, there could be lines that are not of interest because they connect to the corner points. If you pay close attention, you may see a line deviating from the main axis here. And see, these segments were removed by a filtering procedure called spur removal or hair removal. And in this image, you see, if you can pay close attention, a single pixel thick line that corresponds to the skeleton or medial axis of the convex hull. Now, this was extended and superimposed on the result of detection of the vertebral plateaus. The reason or the need for this line is to have a central reference axis for the region covering L1 through L4. So now we have for each vertebra the central line. This helps in making measurements of the thickness as shown in this picture, where the central part of the axis is shown here, which is not a straight line. The points of intersection of this line within this particular vertebra, delimited by the plateau shown at the top here and the bottom here. The points of intersection were determined and a straight line was fitted between these 2 points, and lines parallel to the new straight line determined were obtained on both sides, and these lines were projected to intersect the edges of the 2 plateaus detected. So these points now give us measurements of the height of the vertebral body at various positions. And there are several such lines. So for each vertebra, there are several height measurements done. And these were grouped into parts that were in the anterior portion, the medial portion, and the posterior portion. And averages were computed, or statistics were computed for these measurements for each region. This is a little difficult to see, perhaps. I don't know if I can zoom. Is it possible to zoom this, make this bigger? You can leave PowerPoint, and then, okay. So here, this plot now, or the series of plots illustrates the differences in the mean height for the entire vertebral body, for the normal group in blue, and for the cases with fractures in red. So as you can see, the mean for all of the vertebral bodies in the normal and abnormal groups differ substantially. And the max values also differ quite a bit. And there is a substantial difference in the minimum value also. The fracture group has a substantially lower minimum value than the normal group. And the standard deviation bars here show that the deviation is fairly small. The lower series of plots or bar graphs show the averages or these statistics for the anterior region, the medial region, and the posterior region for the various vertebrae in the data set. Again, in each case, you have the mean, the minimum, no, that's the maximum, and then the minimum in each group. So in all cases, it is evident that the measurements are substantially lower for the cases with the fracture in red than for the corresponding cases or the measurements in blue for the normal cases. Now we are still we are continuing this work, and Eduardo is going to derive p-values for statistical significance of these differences. We will also compute additional statistical measures such as standard deviation or variation or variance or coefficient of variation and so on to characterize the effect of fracture on the height of the vertebral bodies. The analysis done at this stage in the work labeled all the vertebrae belonging to the patient group as abnormal, although some of them might not have had a fracture, correct? So what we are doing next, Dr. Marcelo Nogueira Barbosa, is labeling the individual vertebrae or each vertebra as being normal or fractured, and this analysis will be repeated on a per vertebra basis. And the statistics derived will be used to classify each vertebra as normal or not. So this is work in progress. There is some more work to be done to improve the segmentation of the plateaus. We have another procedure that Eduardo has developed in which the entire vertebral body is segmented and detected. We may be able to get better results by detecting the entire vertebral body and then detecting their edges rather than trying to detect the plateaus only. But we are still experimenting with a few different options. And once the vertebrae or their plateaus are detected, measurements such as these become possible, and further statistical measures of variation of the height of each vertebral body could be derived. And such measures could be used to classify each vertebra as normal or not. This is where we are at this stage, and the work is still progressing. Eduardo is planning on completing his master's thesis over the next 6 months, 8 months, before the end of the year. And then next year he's planning on continuing for his PhD on this topic, and hopefully the results will keep improving. So the results obtained so far indicate that the proposed methods or the methods that we have developed can provide accurate results of segmentation to the level of accuracy that we showed of lumbar vertebral plateaus. And we have another technique where the entire vertebral body is detected with minimal manual input from the user. So in this case, only 5 clicks are required from the user, and these clicks must be positioned, or the mouse must be positioned near the center of each disc between L1 through L4. For the case of training and validation, we do require the radiologist to label the vertebral bodies or the vertebral plateaus, but that is used only for training. The methods are being evaluated, or there are plans to evaluate the methods with a larger database, and a number of cases have been identified for further testing and evaluation. And we have a few more thoughts on how to improve the results of segmentation and derive measures related to various types of vertebral deformities. This work is in progress. So we thank the funding agencies identified here, and thank you for your attention. If you have any questions, we'll try to answer them. Obrigado.